Awesome. Thank you so much, everybody, for having me. Emmanuel Ehrman. I'm a neurologist in the anesthesia department at UCSD. I've been in this space since 2012 when I started my research work on vagus nerve stimulation and understanding the effects of vagus nerve stimulation. And over the years, I definitely saw that different things worked in different people. And that was the genesis for my work now. And so the company that we formed is through a BARDA contract through the DRIVE program. And essentially, with that project, we put forward a inflammatory model called lipopolysaccharide. So we inject humans with LPS to see their inflammatory response. You may ask, well, what's the value of that? Well, in our mind, there's a huge value, especially when you're talking about the autonomic nervous system. You can start to understand many different factors, many different components of the autonomic nervous system that essentially change in concert at the exact same time in every single subject. What's different, though, and what's amazing is that between subjects, there are differences in the magnitude of these changes. And we can start to understand who may have more of these changes before they even have this LPS injection. So biotyping or endotyping patients is what we're very interested in. And I'll just talk about some of the things we're doing today in this work, but we're interested in all of these factors. So we do magnetoencephalography, we do EGG, we do electromagnetography with optically pumped magnetometers. And we record this peripheral nerve activity with optically pumped magnetometers and cervical electroneurography with electrodes that we've developed. So what is LPS? It's a component of gram-negative bacteria from E. coli. It acts on toll-like 4 receptors. I think many of you are aware of this pathway that essentially results in immune cells releasing lots of cytokines. Again, what's so interesting is these cytokines go up in crescendo in sequence. Right. And so you can see TNF go up and then IL-1 and then IL-6 and then IL-8 and then interferon gamma. So it's very sequential in its form factor. And we record, again, all these different components here. So it's different. Like I said, it's different. The response is different between people. This is a subject that had PTSD, and this is his response at 1 hour time point when everybody has maximal symptoms. Okay. So okay, presentation failed. Next guy is does not have mental health disorder, all right? So his autonomic tone, his autonomic disposition, at the same time point, his cytokines and his neural firing that we recorded was much different than others. So our goal is to identify these factors in humans. We look at multiple different systems. We see when these networks may be in tandem. So is there changes in the gut motility that's syncing up with slow waves in the brain? Are there changes in these neural firing patterns? And we've recently just developed an AI-powered EMR system. So we have a system model that extracts out all electronic healthcare record of every inpatient at UCSD. We're also getting ready to run at the University of Minnesota. And then we've looked at 10 million patients encounters in the past and seen, okay, when does somebody have inflammation? And the way we look at inflammation is whether or not they have a diagnosis of sepsis. So our goal is to identify patients at high risk for sepsis as their first use case scenario. And Victor asked me to talk about time series and what's important in these different types of measurements. Again, we measure at 16 kilohertz to get action potentials and record these action potentials with our optically pumped magnetometers and our electrodes at the neck. But we're also looking at a lot of other time series. So the heart rate, the respiration, the gut movement, and amongst different pathogens, like I said, with E. coli, at 60 minutes, they have their maximal symptoms, right? And then they go away. Everybody goes away after 6 hours. All their symptoms go away, all their cytokines reduce, and their neural firing goes down. It's a conserved temporal incident, right? Different pathogens can have different periods of time that it takes for them to coordinate immune response, right? So the host response can take different amounts of time for different pathogens that you can actually right now just look at temperature in the hospital and differentiate, say, gram-negative bacteria from gram-positive bacteria. So our goal is to look at these system models to predict pathogen-specific disease severity. We've brought together these different neural sensing mechanisms. This is a picture of the actual prototype that we've developed. This is now in humans at our hospital. We're running a feasibility trial. And in addition to the just running our models at UCSD, we want to run our models at each hospital. So to do that, you can put together everybody's data in what's called open federated learning. And I can take every hospital's data set, put it into a privacy preserving convened consortia, and then essentially run our models all together and generalize them with much higher sensitivity and specificity. So that's the open federated learning. Why is it important? If somebody has sepsis, every 1 hour, they have an increase in mortality rate of up to 7%, right? So as soon as the doctor diagnoses somebody with sepsis, they don't have very much of a runway before they are deceased. So if we can identify that they have this inflammation occurring before that period of time, potentially we can make a big difference. The other thing that we're working on is and this is a closed loop talk, right? So we're very interested in neuromodulation in addition to just sensing, is can we use this model to test your device, right? Can I take a look at your anti-inflammatory effects with our sensing mechanisms? And we're doing that right now. So we have multiple different devices and companies that we're working with. We do focused ultrasound to the spleen. We're going to do focused ultrasound to the cholinergic forebrain. We recorded with MEG in the brain during LPS, and we see cholinergic forebrain nuclei light up. So afferent vagus fibers going to the cholinergic forebrain activate, which you would expect them to during this LPS procedure. The idea is, can we differentiate these endotypes? This is where we are at the moment. Again, we have some non-dilutive funding that's in process, and we're going for a BARDA Plus program. This is our team, and I'll end there. How much time did I go over there? Are there any questions?